Hello, everybody. Welcome to Blue Marble Science. A couple of weeks ago, I met up with Brandon Toy on the Daily Boom. Shout out to Jose JG to answer some questions Brandon had about airplanes. This is that story, and then the rest of the story. Warning! Severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light this dumpster fire and have some fun. Brandon, like many flat earthers, has a hard time believing that our atmosphere is really just an enormous ball of gas that's about 60 miles thick surrounding our planet, and it rotates exactly like our planet does. So an airplane flying in it is being carried along at the rotation of that ball of gas. It's being pushed along just like these airplanes are being pushed along by the winds that occur within the atmosphere. So let's listen to the exchange between Brandon and myself.
All right, guys. We are here and we are currently joining the little improvised combo 1v1 Big Blue versus Brandon Toy. Thank you, gentlemen, for accepting the offer.
Yeah,
thanks, Jose.
Yes, sir.
What's going on, Blue? Yeah, so I wanted to, I chose you because I was thinking we could take it back to Coriolis and flight. I want to get some clarification on one thing that you said a while back, if that'd be okay with you.
Yeah, sure.
All right. Do pilots fly over the Earth as if it is flat and stationary, as if it's a stationary plane?
So pay attention to the questions that Brandon is asking. His questions are to do with the mechanics of flight. Not flight planning, not observations we make while we're flying, but strictly the mechanics of flying the airplane. It's a pretty good discussion. Let's see, do pilots fly over the Earth as if it were a flat, stationary plane? You mean, do we need to take into account the fact that we're flying in a body of air, an atmosphere that is rotating along with the planet? Because as long as you consider it like that, then there's no difference in that constant rotation of the atmosphere and a flat stationary plane.
Right.
I mean,
So
that
in your
yeah.
worldview, oh, did I cut you off? Excuse me.
No, I just that's fine.
So that's a fair enough characterization, right? Since the atmosphere is moving along.
Yeah.
Okay. All right. Thank you. I've had some people question that during discussions about Coriolis, but I appreciate you as a pilot stating that very plainly, or at least agreeing to my characterization with the caveats that you've mentioned. Now, for this trip that we've been talking about for a while, or at least I have, we've discussed it before, from Anchorage to Mexico City, where you're gaining, I think it's about 300 to 400, something like that, miles per hour momentum.
This is the flight Brandon was talking about. It originates up here in Anchorage, Alaska. That's just a little bit north of 60 degrees. And it goes down to Mexico City, down here, a little south of 20 degrees. And that distance is a total of about 3,800 miles. An airliner will make that trip in roughly 6.5 hours. At the same time, because we're changing latitude, the tangential speed of the Earth and the atmosphere increases by about 450 miles per hour. Well, wow, you say, 450 miles an hour. That is a huge increase in speed, and that's what Brandon's been saying. But I want you to think about this. That speed increase takes place over a period of 6.5 hours. 450 miles an hour in 6.5 hours is 70 miles per hour increase in speed. Think about it this way. If you get in your car and you accelerate from 0 to highway speed of 70 miles per hour and you spend an entire hour doing it, do you think you would notice the acceleration? Of course not. And that's why this is simply a red herring.
Did I use the right word, momentum? Or do you want
Well,
me to use another word?
just call it tangential velocity. Okay.
Okay. All right. We'll go with tangential velocity. I've been told that only minor corrections are required along this route in order to stay in lockstep with the rotation of the Earth, the ground speed of the Earth. And I believe you're one of the people who have told me that. Is that correct?
Yeah.
Okay.
Yeah.
So I've heard
those were primarily for. Let me interrupt you for a second. And that would primarily be a correction that we would see as a pilot. You would see it as a wind correction. That's the thing that's most obvious, most measurable, and the thing that's going to cause that you would attribute the deviation in your course and your heading. Okay.
Okay, which you're really not going to notice along the way because, in your words, it's so minor. Such a small correction all along the way that you're not going to know the difference between that and corrections for wind.
No, you'd never notice it, and the atmosphere is doing the yeoman's portion of the work anyway.
Okay, so in your conceptualization of how this works, is the momentum gained via transfer of the wind and to the plane, or is it by turning and transitioning some of your speed to a different vector?
Well, the plane only knows the body of air that it's flying in. Okay, it knows nothing else. It doesn't know anything about the ground speed. It doesn't know anything about the rotation of the Earth. It only knows that it is moving in its frame of reference. It's moving forward in a body of air. Period. So whatever that body of air is doing is what the airplane is doing.
So that momentum is transferred from the body of air to the plane. That increase in momentum, is that right? Kind of getting dragging the plane along, for lack of a better word.
It would have to, wouldn't it? I mean, the plane is fairly light compared to the amount of surface area there. So, yeah, sure.
Okay. Is there a one-to-one transfer of that momentum, or is obviously planes are made to be aerodynamic, so it's not going to transfer all of that momentum to the airplane, would it?
I don't know. I don't know. I would say essentially, yeah, it's totally transferred.
Well, let me probe on that a little bit.
If you think about it that way, yeah.
So if I am flying in a 100-mile-per-hour wind and I turn so that I am with the wind, so the wind's at my back,
Mm-hmm.
and I do nothing else but just steer, is that wind going to carry me along at 100 miles per hour, or will my inertial forces and my aerodynamics keep me from going the full 100 miles per hour?
No, you'll go whatever the wind speed is going.
Okay.
If you have a 10-mile-an-hour wind from your starboard side, you're going to be moving from right to left at 10 miles an hour. Even though you're moving forward at however many hundreds of miles an hour, you're still going to have exactly whatever the wind speed is.
So at that point, if you're moving at the same speed as the wind, your instruments wouldn't register that there is a wind.
Well, you don't have anything to measure wind. That's the thing. There is no instrument that tells you what the wind is. You would never know it. At this point in the discussion, I took a little artistic liberty just to simplify things. Obviously, we have GPS equipment and so forth, and there are ways of determining what the wind speed is if we really want to know it. But we don't have a primary flight instrument that tells us the wind speed or the direction. That has to be computed from the heading we're flying versus the course we're tracking and the ground speed that we have compared to the airspeed that we're flying at. That gets cleared up in a minute.
I thought I read about some kind of pressure device that is on airplanes that measures the wind speed.
Some of the large equipment, and now we're going to get off into things that I can't really talk about because I've never flown large aircraft like that. But on small aircraft, we have nothing on a light twin engine airplane. The stuff I'm qualified to
Sure.
be a pilot of. Nothing in there that tells us directly what the wind speed is. Although some of the more recent GPS stuff that can track your ground, it looks at your actual position over the ground. Keep in mind that for me, recent equipment is anything made after 1980.
Yeah, you'd be able to deduce that there was a wind, right? Because of your ground. Yeah.
Back in the old days, we had a mechanical circular calculator called an E6B, and we could pull that thing out. The back of it would let us work out a wind triangle, and so you could figure out what the equivalent or where the wind was from and what its magnitude was. And you can do that electronically too, but there's no instrument in the airplanes. What I'm saying that says, oh, by the way, the wind's from your right side at 15 miles an hour.
Okay. All right. And one last question on this regarding the actual piloting of the flight. Can you transfer momentum by turning? So you're just changing your overall vector, right? Can you increase your momentum simply by turning?
Increase your momentum. Momentum, of course, is the product of mass and velocity. And really what we're talking about here is not momentum, it's velocity. But Brandon uses momentum and velocity essentially interchangeably, and that's done quite frequently colloquially with people who aren't involved with engineering or physics. So the slight hesitation you heard was me fighting with myself to not become pedantic and correct what he was saying.
Yeah. So if I'm going 100 miles per hour south and I turn to the, southeast, and I transfer some of that momentum in that direction, I'm still going south some right now, but now I'm going in a different vector, right? It's not going to increase my overall momentum. That's the base of the question. Not a great example I just said, but you can't increase your overall momentum simply by turning, right? I'm never going to go above the 100 miles per hour just by turning.
Well, it depends on which speed we're talking about, Brandon. If you're talking about airspeed, no, you can't change it. Your airspeed would remain constant for all intent. There's no change in airspeed, but just simply by turning. But there very well could be a substantial change in your ground speed, depending on what the wind speed is.
Take the wind out of it. Let's say there's no wind.
Okay.
I think you just answered essentially that it wouldn't increase. You'd still have that.
No, it won't. Yeah.
Okay.
Yeah.
Fair enough. All right. So I think I have an understanding of what your model is. So my question would be, using the flight itself and the operation of an airplane, and examples like this, is there any way to falsify what you said and what you say happens in an airplane?
Or to falsify it.
Yes, that you're gaining the momentum and the wind is carrying you along, and that's how you keep up with the Earth as you go south, or that's how your speed decreases as you go north. Is there any way to falsify that model of flight over the rotating globe?
Well, unless somebody can think of a way to stop the atmosphere from rotating, I guess I would have to say no. Never really thought about that, Brandon.
Because those are some pretty interesting claims that are made about how flight works, and you've even said yourself that for all intents and purposes, when you're flying, it's you wouldn't be able to tell the difference between flying over the globe and a flat stationary planes. So that's
No,
why I'm
that's
asking,
right.
because it seems unfalsifiable to me.
That's right. I mean, you have these strange experiences when you fly, especially when you're flying light aircraft, like say a Cessna 150, where you look at your airspeed indicator and it says, "Yes, I'm doing 65 knots." Uh, or 150s are calibrated in miles an hour. I'm doing 60 miles an hour, and then you look out the window and you realize you're going backwards over the ground. And you would never know that if you didn't see if you didn't look out the window, you'd never know that. If you find a day when you've got some really strong winds at say 3 or 4,000 feet, you can literally fly backwards. Uh, and the airplane doesn't know the difference. It has no idea, and you wouldn't have any idea just looking at your instruments, because it only knows the body of air that it flies in. That's all.
Okay.
Fair
enough.
Anything about its relationship to the ground. It's disconnected from the ground. It's simply dependent on what the air mass is that it's in.
Yep. Fair enough. So off the top of your head, you don't know a way to falsify it, I think I heard you say.
Well, I can't off the top of my head come up with anything that would seem to make any sense. You want to wait to prove that the airplane is other than what maybe what I just told you is a way you can do it. You want to wait to prove that the airplane only knows the air that it's flying in, and I just gave you an example of how you can see it doesn't know anything about the ground, or it doesn't know anything about the rotation of the atmosphere, or the wind, or any of that.
Yeah. No, I'll give you that. But I don't think there would be a distinction you could make between the rotating globe model and flat stationary plane model in that case, because you're just concerned with the wind, the body of air, as you said.
Yeah.
Okay.
Well, that's probably true. I mean, I don't know of a good way in an airplane that you would be able to say, "Oh, I'm obviously flying over a curved surface," or "Oh, I'm obviously flying over a flat surface." It could be either. I don't see how it would change the actual operation of the airplane enough that we'd be able to ever know anything about it, really.
Okay.
Now, some of these other experiments that you hear people talk about, and they have been done, and they can be done. Anybody can do them, like measuring the Eötvös effect on eastbound and westbound flights. That shows you some pretty clear evidence that the Earth has to be rotating, or you couldn't have that effect. But
Well,
as far as that's an experiment
that's not true, but go ahead.
Well, it's been measured though, so.
No, I understand the difference has been measured, but as far as pinpointing the cause of that difference, not so sure. But I'm not an expert on that, Bose. So I'll leave that discussion for another day.
This is how conversations with flat earthers typically would go. As long as I am talking about simply piloting the airplane, simply looking at airspeed indicators, altimeters, attitude indicators, vertical speed indicators, and so forth, as long as I'm willing to say simply by looking at that, I can't tell whether the Earth is a sphere or the Earth is flat, and I can't tell whether it's spinning or stationary, they're quite happy with that information. On the other hand, the very moment you bring up another sort of observation that doesn't have anything to do with actually piloting the airplane, that would clearly show that the Earth is rotating or clearly show that it is spherical in nature, they terminate the conversation. Well, a few days after this, I picked up this little tidbit, and I think it deserves a response.
I had a discussion with Blue Marble. I went over to Jose's, I don't know, it was last week or something, and just calmly talked to him about plane flight and asked him, is there any difference? Would a pilot notice any difference? Would you expect the pilot to have to do anything if they were flying over a flat plane as opposed to a spinning globe? And he essentially said, no, there is no way. There's nothing that you can do during the flight. Nothing the pilot does, no sensor or instrument that the pilot uses that will tell you that you're on a spinning globe. It's exactly the same as if you were over a stationary Earth. I mean, it just in plain words.
And in words just as plain, I tried to discuss the Eötvös effect with you, which you hand-waved dismissed, saying that you didn't know what caused it. Well, as the late Paul Harvey would have said, and now the rest of the story. There are a couple of forces that act on every object. One is the gravitational force, and of course, that force acts inward toward the center of the Earth. But a second force that acts on every object is centrifugal force. We're all familiar with centrifugal force. That's that force that makes us feel like we're being pushed toward the car door as we go around a curve. But on Earth, it is simply a result of the rotation of the Earth. Now, there's a couple of things to note about this. Centrifugal force is very easily calculated, and it's nothing more than the mass of an object times its angular velocity squared times its distance from the origin, or the center of rotation, or the axis of the Earth in this case. So the centrifugal force being proportional to the radius is going to be maximum at the equator, because that is the maximum distance it can be from the axis of rotation. In fact, it's going to be equal to that distance times the cosine of its latitude. But it's also dependent on the angular velocity. Now, if the object is sitting stationary on the Earth, it is simply experiencing the angular velocity of the spin of the Earth. But if the object is moving eastward or westward, its angular velocity either adds to or subtracts from the angular velocity of the Earth. So an object moving eastward will have its angular velocity added to the angular velocity of the Earth. That will increase the centrifugal force, and that will reduce the effective weight of the object. But if that same object is moving westward, then its angular velocity is subtracted from the angular velocity of the Earth. That reduces the centrifugal force, and that increases the effective weight. So objects traveling in a westward direction weigh more than objects traveling in an eastward direction. Let's look at a little more practical example. In the mid-latitudes, let's say around the central part of Australia, the tangential speed of the Earth as it rotates is about 850 miles an hour. Now, an aircraft that travels at an airspeed of about 600 miles per hour would have its speed subtracted from the tangential speed of the Earth, and its tangential speed, its rotation around the axis of the Earth, will only be at about 250 miles per hour. On the other hand, the same airplane traveling eastbound will have its airspeed added to the tangential speed of rotation of the Earth, and its tangential speed will be about 1,450 miles per hour. That means that the airplane traveling westbound, rotating slower around the axis of the Earth, will have a lower centrifugal force, and that means it will weigh more than the same airplane traveling eastbound at a higher tangential speed. We have a practical example of this. About a year and a half ago, Wolfie 6020 made two very similar flights to the ones we just discussed, using the same reference mass and the same scale. The reference mass weighed about 5 grams more when it was traveling westbound than it did when it was traveling eastbound. There's only one possible viable explanation for this, and that is the rotation of the Earth. The Earth rotates at 7.292 times 10 to the minus fifth radians per second. I'll leave a link to the video in the description. I highly suggest you watch this. It's something anybody can do for the small cost of the equipment and a round-trip plane ticket. So that's just one of the things I wanted to talk about, but there are others. For instance, how does the sun set below eye level on the flat Earth? That's just not possible. Yet, here it is, and pilots see this every day. And then there's that drop to the horizon. We can use the Alberuni method and find out that it matches perfectly with a sphere that has a radius of 3,959 miles. And of course, there's navigation. You can't make a great circle route work on a flat Earth. It just simply does not. On the other hand, we fly great circle routes every day, and you can't make anything but a great circle route work on a spherical Earth. So before you declare victory and say that we can't determine the shape of the Earth by flying an airplane, think about all the other things that we can do while we are in that airplane. Hey, thanks for watching. And remember, when we ask you guys, how stupid can you be, that isn't a challenge, it's a question. Don't forget to hit the like and subscribe and that little bell down there. Shout out to the Patreons and the PayPals, links up in the description. And I guess we will catch you guys on the next one.